Okay, this is the fourth question of the June 2024 question paper. With the introduction of the new generation of super long stroke engines and changed process parameters triggered by environmental compliant rules, cold corrosion of cylinder liner has grown to become a major issue for the last generation of two stroke engines. So, we need to discuss the causes and the mitigation measures, stressing on the following: an increased jacket water temperature system, A. B. New cylinder liner designs. C. The new cylinder lubricators. Cold corrosion has become a significant issue in the modern super long stroke two stroke engines, especially with the drive towards higher efficiency and stricter IMO compliance, that is the Tier 2, Tier 3 regulations. So, causes of the cold corrosion: low cylinder wall temperatures leads to condensation of sulfuric acid formed from the sulfur in the fuel reacting with the combustion moisture, forming SO3 and water. Condensed acid corrodes the liner surface, especially in the mid-stroke area. So, in the super long stroke cylinders, the mid-stroke area of this cylinder liner has the tendency of cold corrosion happening. That is basically the condensate and the sulfuric acid from the fuel reacting, leading to the surface area corrosions. Increased stroke length. Super long stroke engines uh, result in a longer liner with lower lower uh, lower temperatures being formed at the centermost point, and this results in condensate of the combustion reacting with the sulfuric acid, the sulfur coming from the bunkers, that is HFO, and both of them reacting, resulting in mild corrosion, which is happening in there at the mid-stroke length of uh, the cylinder liner, which is having. Slow steaming, lower load operations reduces exhaust gas temperatures, exacerbating acid condensation risk. So the three reasons here are low cylinder wall temperatures, increased long stroke engines, and also the slow steaming. A increased jacket water temperature system. What happens? What is action being taken here is the role of cold corrosion. Traditionally, the lower cooling water temperatures used to be around 60 to 70 degrees Celsius, which have now been increased to 80 to 85 degrees Celsius. Mitigation strategies: controlled cooling system keeps the liner system above their dew point, which is 135 degrees at cylinder surface. Okay. Uh, So variable cooling system allows adaptive temperature control based on engine load and cylinder conditions. Effectiveness: reduces acid condensation and corrosion. Needs careful control to avoid excessive liner wear on the piston seizure due to higher temperatures. New cylinder liner design: thicker liner wall to withstand higher corrosion wear. Use of high chromium alloyed cast iron for improving corrosion resistance. Mild stroke insulation or controlled temperature zones to maintain optimal thermal profile. Features: anti-polishing rings to prevent deposits built up and acid entrapment. Surface treatment coating like nitride and honing profiles for better oil retention and acid neutralization. So these points are quite important. The design modifications are the thicker liner walls, which can withstand corrosion and wear. The higher amount of chromium that has been alloyed in cast iron to improve the corrosion resistance. mid-stroke insulation and controlled temperature zones to maintain optimal thermal profiles. And also the features that have been incorporated are the anti-polishing rings to prevent deposits built up and acid entrapment, surface temperature coating like nitriding and honing profiles for better oil retention and oil neutralization. Effectiveness: modern liner designs distribute temperatures more evenly and enhance oil film retention, reducing acid attack risk. More resilient to mechanical and chemical wear. Now, with the cylinder liner lubricators, purpose is cylinder oil neutralizes sulfuric acid and provides lubrication. New low sulfur fuel change combustion chemistry entirely, requiring adaptive lubrication. Modern lubricators, electronically controlled lubricators, inject precise oil based on the engine load, sulfur content, and condition of the cylinder. Sensor based backup loop optimizes oil distribution. Lubricant formulation, again, earlier it used to be a higher BR number, that is 7200, used in higher sulfur fuels, and presently with the lower sulfur fuels, BN of 40 or less is effectively being used. So effectiveness reduces corrosion risk while minimizing oil consumption, extends piston ring and liner life. And the conclusion that can be drawn here is the cold corrosion in a modern marine two-stroke engine is primarily driven by the low operating temperatures due to new engine designs and environmental regulations. However, this can effectively be mitigated through higher jacket cooling water temperatures to prevent acid condensation, advanced cylinder liner designs that resist corrosion and retain lubrication, smart lubricator and optimized oils that provide just the right level of acid neutralization. Proper balance and integration of these measures are key to long-term engine reliability and compliance.